All right, let's get going. So here's what we're going to do today. We're going to actually get into Introduction to Sorting, and this is the actual schedule. We will talk about the Unix tip of the day. I think I mentioned this the other day, that there is a way to send email from the command line on the Linux servers, which is kind of cool. And so you can actually do that from our servers here. And I'll show you how to do that with attachments, which is kind of nice as well. Then we'll get into the Introduction to Sorting. Unfortunately, this is another case where I didn't recognize quite how much you had done in the prior class, like Comp 11, for instance. I'm not sure. Did you guys do Comp 50? Did you do much sorting? Maybe a little? Yeah, they did some. There was some done in Comp 11. But we'll get into some more details and talk about complexity and so forth. We're going to talk about a whole bunch of different sorts. Sorting is actually one of my favorite subjects because there's so many different types of sorts, so it's kind of fun. We're going to talk about insertion sort, selection sort, heap sort, which we did kind of in the lab the other day, although we're going to put a little bit of a twist on it. And then we're going to talk about this thing called Shellsort, and if there's any time, we'll go over midterm answers, but I have a feeling there won't be. The midterm, I will definitely go over a bunch of stuff from the midterm on Monday. But if you do have questions about your grades or whatever, feel free to email me now or whatever. There was one question on the mid-year that, again, we messed up the grading. It was my fault. I didn't put it on the rubric correctly. The one where you have to circle whether or not statements are operator equals. There was one extra one that one of the TAs took off like points on if you circled it, and she said, oh, it wasn't, but it turns out it was, and that was my fault. So what I'll do is I'll go back through and fix all those. So many of you will probably get 1 point back on that if you circled something in it, or you didn't. Yeah, if you circled something and you got points off. Okay, any questions before I get going? All right. Oh, and then, by the way, at the end, we'll talk about the next assignment, which is going to be out tomorrow. So, and it happens to be on sorting. So we'll get there. OK, so as I said, you can send mail using Linux, right? Well, if your Linux server happens to have a mail server on it, which ours does. And here's how you do it. You can actually say, and you can type this. I'll show you in a minute. You can type mail-s and then a subject, and then the email address that you want to send it to, and hit return. And then it will present you with a blank line and basically be waiting for your input. And then you type an email, type Control-D on a blank line, and then it will send the email. That's it. Kind of straightforward. OK? You actually, you can put a CC in there as well. Let me show you. For those of you writing it down, I'll flash this up again in a minute. Oops, I've got to take out the trash. Hang on a sec. In fact, yeah. All right. So let's see. There we go. So let's say I type the following. Mail-s, quote, howdy Chris, and then an email address. Like I'm going to send this to myself. Right? And then I hit return. Well, it's just kind of waiting for more input. And I can say something like, hey, Chris, sorting is a blast. Right? All right. And then I go to the next line, and I hit Control-D, and then there's a little CC that comes up, and I could type somebody else's email address, right? And then I just hit return, and that's all it does. It doesn't actually tell you anything. It just like sends your email. So now I'll get an email in a couple of minutes on my computer here. OK? Pretty straightforward. Yes?
Who would the email address be from?
It's from your username, probably at cs.tufts.edu. So it's probably your CS username. And you guys, I don't know if you know you had CS user accounts like that have emails associated with them. If you didn't know that, you should probably go in and forward any emails from that to your regular Tufts email or whatever other email you want, just in case anybody sends you something there. Not that they necessarily would, but that happens to be my main email address is the CS one. Yes, Lydia. Yeah, how do you set it up for forward? Good question. I believe if you go on to the, let's see, if you go to like webmail.cs.tufts.edu, I think there's a place where you can say forward mail to some other address, and it should just blast it out there. You probably, like I said, you probably don't have any emails, but that's that. OK, questions on that? That's like the simple way of sending mail, right? Now, if you want to send if you actually want to send an attachment, you can't use mail. Unfortunately, it's too simple to allow attachments for whatever reason. So there's another way. There's a program called Mutt, and I forget what it stands for. I'll check in a sec. But here's what you do with Mutt. You say Mutt, the -x is basically saying, give me a very rudimentary editing screen. If you don't type the -x, it will pop up whatever editor you normally use. Well, whatever editor is set up. Most of the time it's VI. So if you don't use VI, you'll get a VI window, and then you'll have to go searching the internet how to quit if you forget how to quit. Right? But if you type the -x, it gives you a rudimentary one. The -a says, give me an attachment, or attach the following file. In this case, file.zip. And then the -s for subject, same thing, and then the email address. So it's more or less the same thing, except with this -x in here and the file name. And you actually end it slightly differently with Mutt too. For whatever reason, Mutt says, put a period on its own line and then hit return, and it will say, oh, that's the end of your message. I don't know why they did it that way. But, oops, let's see. Let's take a look here. OK, so if I do this, here we go. Mutt-x, actually, let me see. There you go. Mutt-x -a readme.txt, and then -s, and then the subject, and then my username, or the username where you're sending the email. And then you hit return. It actually pulls up this window, but you're actually typing down at the bottom for some reason. So here's a great attachment about how fun sorting is. Whatever, right? OK, and then you hit return, and then you continue to do your email. And then if you put a period and then return, it sends your email. OK? And that was it. That was it. OK, questions on that? Pretty simple. You can, if you don't, we tried this in the other class. If the README file doesn't exist, or the attachment doesn't exist, it'll just tell you that. It'll say, hey, look, I can't attach the file. But that's that. OK, so if you want to send yourself email or send some other people's emails, I did that for a couple people in labs where I said, hey, send me an email. Oh, let's just do it right now. Boom. And then knocked it out. Pretty simple. OK, questions? All right, awesome. Where were we here? There we go. OK. That's the Unix tip of the day. All right, so now we're going to get into, like I said, one of my favorite subjects here. We have already discussed sorted lists to some extent, right? Our first couple of assignments, we had to insert into a list in a sorted order, right? So we've already talked a little bit about some sorts of sorts, no pun intended. But it's one of those things that, one of the reasons I like it so much is because there are a zillion type of sorts. Like you can figure out lots of different ways to order elements inside of some structure. And not only that, there's actually some open problems in sorting. People every so often come up with new types of sorts that have never been described before, and they turn out to be pretty good. If you've ever programmed in the Python language, the Python default sorting algorithm is this algorithm who this guy named Tim created like about 10 years ago or so. And some people who write the Python language found out about it and said, hey, this is actually a pretty cool sort. We'll use this instead of whatever other sort they were using. So it's pretty efficient. And they actually call it Tim Sort, because that's his name, right? But that's a relatively recent phenomenon. I mean, we've been sorting stuff forever, right? It's like the computers have been sorting stuff since the first computers in like the 40s and 50s. But we're still having some open problems. We'll actually talk about a type of sort where it's still undetermined what the average complexity is of the sort. Still undetermined, right? So kind of cool stuff. All right, so sorting consists of what? Sorting, at the basic level, sorting is just put elements in some order, okay? Often in either a numerical order, ascending or descending, depending on how you want to order it, or in a lexicographical order, in other words, alphabetically, like you're sorting words and things, okay, like we did in the lab the other day. Okay, that's the kind of the basic idea of sorting, right? Not like rocket science. In order for a list to be sorted, you have to do what we call, and this is an odd one, we say it has, the sorted items must be in a non-decreasing order. Well, why wouldn't you just say increasing? Well, I don't know. But what that means is each element must be no smaller than the previous one if you're ordering in that direction. I guess it would be non-increasing if you're ordering the other direction. But that's really the only idea. And it goes back to this idea of, hey, you need to be able to compare elements for sorting. Not all sorts are comparison sorts. We'll get to that in a little bit. But the idea is they have to be in this what we call non-decreasing order, and then they're sorted. And they also have to be some permutation of the input. You can't say that you're changing keys or changing things when you're sorting. Like you can't say, oh, well, I'm going to change the key of this and now it's sorted. No, it's got to be the same key to the same item. Then it becomes a sorted list. It's got to be some permutation. Yes?
Can you explain the first bullet point?
The first bullet point is just like boilerplate. It basically just says, look, they are in this order that's determined by whatever comparison you have or whatever other idea. So it's just saying you can't have, and if you're sorting in this case from greatest to least, right? You can't have elements that are still not greatest to least in whatever your ordering is. So it also takes into consideration keys that are the same. So if you have 2 5s in your list, well, they can be next. They just have to be next to each other in that sense. Okay? We'll get into where that becomes important in a little bit as well. All right? Anything else on this one? This is not too tricky, I hope. All right. As I said, sorting's very well researched. Okay, this guy Tim came up with his algorithm in 2002. That is recent memory. All of you guys were born then, I think, right? And fundamentally, the first types of sorts we're going to talk about are these comparison sorts, where you're comparing 2 items, then making a decision on where they go based on that comparison. Fundamentally, you're not going to get any better than order n log n. Okay, that is provable. That for comparison type sorts, you can't get better than n log n. There are other sorts where you can do better than that. In fact, I think it was in the morning class last week, or on Monday rather, somebody said, and I might have mentioned this the other day, somebody said, hey, what if we have a sort that takes let's say we're sorting integers, and what if we took an integer and just put that integer at its index in an array? Like let's say we're sorting 1, 7, 2, 4, 6. Element 1 would go at position 1 in the element, right? In the index. Element 6 would go at position index 6. It's an interesting way of doing it, right? You've got to do that. You can do that. What's the complexity for that kind of sort? Yeah. Not O1, because you do have to go through all the elements, but it's order n. And you go, oh, look, we found an order n sort, right? What's the problem with that sort? What is it? That is one problem. If you have the same number twice, that's a problem. You all of a sudden have to, you'll double up on that. Yep. What's another one? Yeah. Check.
If you have an element that's bigger than the capacity?
Yeah. What if you were sorting 1, 3, 7, 12, and 4 million? Right? All of a sudden 4 million. You need to have an array that's got a 4 millionth index in it, right? So yeah, all of a sudden you're running into this weird space kind of complexity issue too. So that's actually called a bucket sort, and there's various types of bucket sorts, but it's an interesting one in that you can sort very fast using it. So for what it's worth. So let's see. And here we go right here. We do have to consider the space complexity. In other words, when we're talking about the complexity of these algorithms, we have to think about, okay, how much time does it take? Best case, worst case. We'll mention average case, and then also, how much extra memory does it take, right? We're going to get into some sorting algorithms that don't take any extra memory. They're called in place. I think that might be the next slide, where you just permute the whatever array or structure you've got it in such that you don't have an extra amount of space. When we did the heap sort in lab over the last couple of days, you may not have noticed it. I'll put the code up in a little bit, but we actually created our heap, and then as we removed all the minimum elements, we put those elements into a whole nother array and took up that much more space in doing so. In fact, we used 2 arrays. I'm not exactly sure why. But the point is that instead of having just n amount of space, we needed now 2n amount of space. And sometimes that makes a huge difference. Why? If you're dealing with billions of items, you don't want to have to allocate all that space, and you don't want to have to make sure you have the availability of it. So space complexity is another key portion of sorting. Okay? All right. This is what I mean when I say, this is a slightly different idea, stable sorting. in-place sorting, which we talked about, in-place sorting, can be either what we call stable or unstable. Okay? What that means is a stable sort retains the order of elements with the same key. So for instance, let's say you have two 5s in your elements that you're going to sort. If this 5 comes before this 5 in the original array, after it's sorted, if it's a stable sort, this 5 will still come before this 5. Now you think, why does it matter? Well, if the 5s are just keys, maybe there is some other reason you want to do that, right? Sometimes you want to you want to make sure that the order doesn't actually swap for your. There might be some other key sort of metric that you're trying to worry about. But that's when we talk about a stable sort and unstable sort. That means that some unstable ones can actually swap the order of equal elements as you move along doing that sorting algorithm. Okay? So we're going to have a couple of different lectures on sorts. There are a couple great sorting animation websites that you should try to look at. I'll show you a couple in a second. There's one called, there's this sortingalgorithms.com, which I'll go to in a sec. And then there's the one we've been using for class recently, which is just the regular visualizations. That presents some of them in a slightly different way, which might be more easy to understand. And then there's actually a very cool video here called 15 sorts in 6 minutes. I'll show you that in a sec too. And then I'll show you that right after we do a couple of the first sorts. Show you part of it anyway. And that one's kind of really neat because it also includes sound, which is kind of neat. So we'll get to there. So anyway, you can look through these and we'll see what they look like. All right. So this is a sort. The first one we're going to talk about is insertion sort. Now we've already covered this for the most part. Okay? Insertion sort is the one where you're inserting into a list, you find out where it goes, and then you move everything out of the way and put it right where it goes. If we want to do this in place, in other words, we've got an unsorted array, and we want to actually do the movements in place so that they don't use extra memory, all right, we have to think about it in a slightly different way. Okay? Let's figure out how to do that. Okay. Actually, anybody have any idea how we would do an insertion sort without wasting extra memory? You want to think about it for a sec? We do an insertion sort. In other words, take an element, go through the list, find an element that where some element needs to go, and then instead of like pulling it out and moving everything over, how might we deal with that? Yeah, Sam?
Could you just start at the first one and go through and find the smallest, flip them?
Find the smallest and flip the first and the last. Yeah, that's it.
Find the smallest and flip it with the first one.
Find the smallest and flip it with the first one. That is a good way. That's actually not insertion sort, though. It's actually a slightly different sort. We'll see in a sec. But good idea. Good idea. But I like your idea of swapping. Okay? Here's what we're actually going to do. Okay? We're going to start at the second element. The first one is already, we're not going to compare it to anything before it, because it's kind of trivially sorted in the sense that if it was the only one on the list, it would be sorted. But we're going to start with the second one here, and we're going to say, look, compare it to your neighbor, actually. And if your neighbor is less than, or if your neighbor is greater than you, we're going to sort an ascending order in this case. Later we'll see a descending order one. So in other words, the lowest elements go over here. So if what we're going to do is we're going to say, is 5 less than 9, swap there. And then keep going back until you don't need to swap anymore. Okay? Yes? It is an insertion sort because you're finding the next, you're going down the list, you're getting to the next one and inserting it in the right place. Now, yes, you're doing swap, 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 but really what you're really doing is moving everybody over one and then putting it where it needs to go. Yeah, Lydia.
What's the criterion for like the proper place?
Good question. Whatever as you go backwards, whenever you, so for instance, because we're doing it in the order we're doing, right? What we're going to do is we're going to say 5 swaps with 9, and then 9 ends up here, right? Okay, and then, because we're going smallest to largest, yeah, in this case. Is that your question? Just smallest to largest in this case? Oh, yeah, we're going smallest to largest. Then we're going to go and we're going to get to the next one, right? And we're going to see if we want to swap it. And then if that one also needs to swap, you'll need to swap it. So you'll see how it works. So you'll actually get to a variable, and then what will happen is as you go back down, you'll either hit one that because everything before you is already sorted, you'll get to the right place when you need to. Yeah? Yeah, good question. Does the swapping itself take an extra memory spot? Yes, it does take an extra memory spot to swap. What we're not doing, though, is we're not pulling it out and then scanning back and scanning through to find where it goes. We could do that. In fact, that would still be an insertion sort. But this way is kind of a little more, yes, you do need an extra spot, but in some sense, I guess maybe it seems a little simpler in some sense. But it's not really as efficient as it could be. Absolutely. Yeah. Other questions? OK. So you iterate through the list, starting with the second one, add each element, swap with its previous neighbor, repeating down until the element's in its proper place. And you'll see that you won't stop too early or go too far when we get through this. OK? So let's see. So first we start with 5. It needs to swap with 9. OK? And this is our placeholder for the iteration that we're going through. OK? All right, we get to 10. 10 actually doesn't need to swap. 9's already less than 10. OK? 8 does need to swap. OK, so we swap that. And then it also needs to swap with 9. So you need to keep going backwards and swapping along until you find the one that needs to go to. And then 12 doesn't need to swap. 11 does need to swap. 14 does not need to swap. And then we get to 2. Right? And 2 is like, look, I got to swap with this one, then 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 this one, and then this one, all the way back to the back, all the way back to the front, all the way to the front. Right? So it gets kind of ugly in that sense. There are times when this is not very good. And this is the exact same thing we found when we were doing insertion sort before, right? If you found out that an element was, if it was near the beginning, you had to move everything from that near the beginning spot over 1. And that took some time. Okay. And then finally, we get to 22, because we've moved 2 all the way down here. And then we get to 22, and 22 doesn't need to swap, and 43 doesn't need to swap. Okay? That's insertion sort. What is the complexity here? Well, the worst case performance complexity is n squared. In other words, every single time you go through, you find that you have to swap everybody else behind you. Right? Because if it was in some sort of like reversed order, you'd be in trouble. The best performance is if you don't have to do any swaps. If it's already sorted, you walk through the whole list, you don't need to make any swaps, and you're done. Okay? And these should be similar to what we had before when we were talking about how to do our sorted array. Average performance, n squared, not so good. But as it turns out, when you have a small array, it is actually very fast. Why? Because there's just not that many elements in there. Okay? What question does that bring up? What is small? Yeah, exactly. What is small? Well, turns out that small in general, and by the way, the reason this makes a difference is some algorithms get to a point where those algorithms, because of how complex they are, would make sorting small arrays longer. So what they do is they get to that minimum, or that kind of small, and then they say, just go do an insertion sort. They switch gears and go do an insertion sort. So in this case, small is found empirically, depending on your sort. You generally write a sort and then try it out for a whole bunch of different inputs. Generally, we have between 5 and 15 is when they consider small. So anything below about 15 elements, you can do an insertion sort, and you will not be losing any time overall. And it's probably better than some other type of sort that you're already doing because of its complexity. Okay, so a lot of sorts do that. Space complexity, we are only order n because we don't have to actually create any more arrays or do all that. You do have to have 1 extra for swapping. So you're going to get that either way. If you want to do it more efficiently, pull it out, find out where it goes, move everybody over, and then plop it in. Probably less time than actually doing the swapping. Okay? I forgot, I was going to show you the website. Let's see. There it is. I want to show you the sorting algorithms website because it is pretty fun. So here's a bunch of sorts here, right? The insertion one we just talked about. The selection we'll talk about in a minute. Bubble sort, don't use bubble sort. Okay, I don't know if you guys have coded bubble sort before, but it's a terrible sort. In fact, I'm not the only one that believes this, right? I found this video today. Some of you might have seen it before. Let's see, what was it called? YouTube. No, here's what I'll do. I'll go to. I thought I already brought it up. Programming. Whoops. And then we will do sorting, something like that. Nope. Ah, hang on. Let's see, where did it go here? Nope. Okay, hold on. Obama. You'll see why in a second. Here we go. Obama on sorting 32-bit integers. He was at Google before he became president. Hang on, I'm going to turn the lights off. There we go. Oh no, it's not loud enough. Ah.
Yeah, the YouTube volume is low.
It is? Oh, sorry, hold on. No, it's still not good. Hang on. All right. There we go.
We have questions, and we asked our candidates questions, and this one is from Larry Schwimmer. So, what, you guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 briefly integers?
Well,
maybe, I'm sorry, maybe.
I think the bubble sort would be the wrong way to go.
Right?
Come on, who told him this? Okay. I didn't see computer science in your background.
We've got our spies in there.
The bubble sort is the wrong way to go from the President of the United States of America. So, you know. So yeah, don't do bubble. And it really is a terrible algorithm, so for what it's worth. So anyway, so this is actually a very cool website. So here's how it works. This is, you'll notice these are all the same order for these things. These ones are all the same, and this one's all the same down here, and this one's all the same. And what it is the little lines here are the smaller integers, and then the bigger lines are the bigger integers. And what we want is it to be sorted. Like this one's almost sorted, right? Okay, it's nearly sorted. And this makes a difference. Like if you're sorting random integers, some sorts work better on random like arrays. Some work better on things that are almost sorted already. Some work better on reversed. Well, not many work. Well, some do. Some work okay on reversed. And then some work. This one's if like this one and this one and this one are all the same size. So some work a little better if you've got the exact same size. And you can tell. You can't tell in this case, but whether or not it's able to sort them in order, if it's stable or not. Okay, so watch what happens when I click this big button here, right? Right? So what it's doing is it's sorting these, and you can tell that some are faster. Like quicksort's already done. Bubble sort's like horrible, right? Although it actually is okay. It's actually a little better than our selection sort, which we'll get to in a minute. Okay, I'm not exactly sure why in this case, but you can see that. So it's kind of cool, right? You can actually go in there. So the one we just did was insertion sort. You can actually click on here and then see a much bigger type or problems. You can change the problem size. You can make them bigger. You can actually read the algorithm in here, right? And by the way, this may be important for your upcoming homework assignment where you're going to have to write some rudimentary sort algorithms. You can look at the algorithm here, okay? And then you can see what it. Oops. You can. Let's go back here a sec. You can see what it does there like that. So this one's a little bit too fast to actually like figure out what's going on, but you can kind of get a feel for the idea of it. And you can definitely tell if it works better or worse on sorted or not sorted sorts of things. Okay? And you can tell, look at this, the insertion, it has to go all the way back down and like, propagate all the way through before it gets sorted. Okay? Sorry, I really should turn this off. Okay, Jennifer, if you're here, I'll see you at 5:30. No, 6. No, 5:30. I think you said it. Okay, anyway. Okay, so that's the sorts. Okay. All right. Let me turn the lights back on. There it is. Sorry. OK, so we went through insertion sort, and then we now have selection sort. Now, I don't know if you remember, the selection sort was kind of a terrible sort as well. But it's a very easy one to write, so I'll at least show it to you here. Okay? Selection sort also can be in place. Okay? And what you do here is you go through the whole list, find the smallest item, and exchange it with the leftmost unsorted element, which is exactly what Sam was talking about earlier, right? Said find the smallest, go through the whole list, find the smallest, and then exchange it with the first one that you haven't sorted yet, basically. Okay? You keep a placeholder of where you've already sorted. Okay? And then you repeat the process from this first unsorted element. Okay? This one, well, I can show you the animation. I'll show you that in a minute. This is how I did it up here. Okay, it's particularly slow. Not a very good one, and you saw that in the other animation, right? So here's what we do. Here's where we're going to put it, right? If you go through the list, 2 is the first one. So you have to scan through the whole list, find 2, and then swap 2 with the first unsorted one. So 9 will go here and 2 will go there, like that, right? Then you go through and you find, oh, it's 5, and oh, good, it don't have to actually swap here because it is the smallest one already. And then for 10, it's 8, et cetera, et cetera. I'm not going to make you go through the whole list here, right? But the complexity here, the worst case is n squared. The best case is n squared, right? You still have to go through everybody, and then you actually have to, you have to do the swapping at the beginning, right? So it's, I mean, you may not actually have to swap, but you have to go through the motion of going through everybody, that many times. Okay, you have to go through n number of times. Okay, average performance n squared. It's terrible. Okay, space complexity though, not so bad. It's order n total. It doesn't actually. We do it all in place. It's all just swapping in place. So relatively straightforward in that sense. Okay, questions on selection sort? Not a very hard one, I don't think. Okay, actually, this is a good chance for me to show you the other cool video that, let's see, whoops, yeah, there we go. Let's see, the other cool video, oh no, you don't need to do, hang on. You need to find it back up here, sorry. I should have opened it up before. Oh, it might already be open, but I don't know. There. The 15 sorts in 6 minutes. This is a fun video. Right? Why is it fun? Because it has sound and because it does actually show you how this whole sorting thing works pretty well. There it is. Okay. This is selection sort. Whoa, okay. What it's doing is the smaller the value, the higher or the lower the pitch of what it does. And when it swaps, it does both pitches. This one's insertion sort. There's more values here. It takes a little longer. But you can kind of see what's going on, right? Make it bigger. All right. So there's a lot here. We'll do some more. This one's quick sort. Whoa, quick sort's weird, right? We'll get to what quick sort looks like, right? Yeah, quick sort's got lots of, jumping back and forth. Bing, right? Woohoo. All right. Let's see. Merge sort. We're going to talk about that later. This one is called merge sort. Anybody want to guess what the order, the complexity is? There's a log n in there somewhere because you can tell it's breaking things in half, right? Boom, right? All right. I'll show you some of the other ones. This is Heapsort, which we're going to talk about actually now. All right, I'll wait on that one. OK, so there it is, Heapsort. OK, so we've already kind of covered Heapsort in some sense. All right, Heapsort was, as I said before, we did not efficiently do Heapsort before. In other words, we took our heap, we heapified some array, and then once it was a heap, then we said, all right, copy into a brand new array by doing remove min all the way through the array, or all the way through the heap, right? So that actually just that took a whole nother array of n items and put it in there. And then for some reason we do another one. I think it's the one we want to return. For some reason, I don't know why we just didn't do it up here, but it didn't actually matter because our list was so short. But we can do heap sort in place. Okay? All right. Now, here's what we have to do. First, do the heapify. Now, we already knew that. That's what we did in the lab, right? You did build heap. You wrote that function. And remember how build heap worked? You remember how that one worked from the lab? You had this unsorted array, and then you built the heap out of it. Yeah?
Yeah, we went to the first parent, right? We
Went to the first parent, bubble it down, and
repeat
repeat for all the other ones with children. Yep, that's exactly it. And then you've got a heap. And now it's in heap form. Is it sorted? It is not. It's heap. It's sorted in the terms of the heap. It is a heap in that it has the heap property of all the parents, or the parents have higher priority than their children. But it is not sorted, and I'll show you an example of why that makes a difference in a second. Okay, once you've got a heap, we are going to iterate over the whole array, and we're going to do the remove min. But instead of like returning the value that we removed, where are we going to put it?
You're going to put it in what is going to be the sorted array.
You're going to put it in, you're going to put it in, it's like in the same array at the location that you just freed up, which happened to be which location? Not one. Not the top one. I'll show you. Which location, when we remove, and remember when we did remove min, we took away the root and we returned it. What goes in the root's position? The last one. That goes there. Then what was the one thing we had to remember before we did down heap? Heap size minus 1, right? So that heap size minus 1 means that element is now free. Well, what are you going to put there? The thing that we just took off the minimum. And if we keep doing that, right, we will end up with kind of a reverse sorted array, right? It will be from maximum to minimum instead of from minimum to maximum, which is fine. If you wanted to make it minimum to maximum, build a max heap and do this same process, right? Yeah?
You still need to keep track of, you still need to lower heap count because part of it, when you put the last element on top, you then have to bubble down. You don't want to bubble down into the pieces you're putting in order at the end of the array.
Yes, exactly. You do have to make the heap one element smaller each time. Yeah. But that happens by default when you're doing remove min. Now, I mean, you would rewrite, if you were doing heap sort in general, you would, for the in place, you would rewrite it slightly just to do this swap instead of doing the return. That's the only difference, which is nice. And at the end, you will have a sorted array, backwards sorted, but sorted, backwards from your priorities. Okay? And that's what it's going to be. Now, let me show you this. There were some, in the last class, there were definitely some questions about this one, which we can hopefully rectify here. Okay. First things first. We start with something that's completely unsorted array, and we heapify it. And that was what we just talked about, where we go to the first one that has a child, and then we bubble it down. Then we go to the second one that has a child, and we bubble it down, and so on and so on. So on and so forth. When you do that, you end up with a heap. Now, is there a way to go through the elements one by one and pick out the proper order? Not efficiently. Okay? Not efficiently at all, in fact, without doing some other work involved. In fact, here's a good question for you. In a heap, we know what the minimum element is. What's the second minimum element? Is it always a left tree? Not only, in this case it happens to be, because 5 is less than 10, but 10 and 5 could be swapped and you'd still have a heap. Okay, in fact, in this case, you would not quite still have a heap if that was like 7. 7 and 5 could be swapped, and it would work.
Would it be one
right?
of its children?
It would be one of its children, sure. So the second element in the second minimum element in a heap is one of its children. So you just have to check 2 children. But then how do you do the third minimum element in a heap? Well, not necessarily the other child. It's one of the 3, right? I mean, well, are there 3 at that point? I mean, I guess there's
Child, so you would have the
child of the 2 children here and the 1 child that you didn't check before. Yeah, so it's going to be one of those, right? So yeah, the algorithm to actually find like the third and fourth and fifth minimum one, not trivial. I mean, you have to think, it's possible, but it's not trivial. And it's much easier to do than trying to write that algorithm to just do what we're about to do. Okay? All right, so you've heapified it. Now this is a heap. We've got it in a heap. It follows all the heap properties. The children are lower priority than their parent, and it's a complete tree. Okay, so we're good to go there. And you just start going down. So what you do is you say, fine, call remove min. Take 2 and swap the root with the last element. So 2 and 43 are going to swap. And 2 is going to go right there. And then we are going to say the heap is 1 less. We're going to decrease heap size, or heap count, or heap size, I guess is what we called it. And then we're going to bubble down 43 like we would do normally. Okay, like the following. 43 is going to be up here. 2 is going to be down here. I've colored it green to say, hey, it's not part of the heap anymore. Okay, why is it not part of the heap? Because it was just replaced there, and the heap is now 1 fewer. The only reason we get to use the space there is because it's like free space. I mean, it's the heap is now this big instead of with that extra little 2 in there. Just there's our extra space. Let's use it. Okay. So now we have to bubble down 43. 43 is going to go boop, 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 all the way down to here, actually. And then the 5 is going to end up here at the root. 8 is going to up here, and 9 is going to end up there, like that. Okay. And then now we're on this. Now the heap size is here, and 5 is now going to is the root. So we swap 5 and 22. Right. Swap 5 and 22, and then bubble down 22. But 5 is no longer in the heap. Got to keep that in mind. 5 is no longer in the heap. 22 is going to go boop, boop, and end up there. And then 8 is going to end up as the minimum value. Okay. All right. Let's try another one. 43 and 8. All right. 8 and 43 swap. Right. And now 8 doesn't even exist in the heap anymore. You have to bubble down 43. It's going to go this way. Then it happens to go this way. Right? And it can't go to 2 because 2 doesn't exist in the heap. It's going to go boop, boop, and end up 43 there, 12 there, and 9 there. Good? All right. And then once we do this, now we've got, oops, I forgot to take away the little arrows, 14 and 9. Right? Because 14 is now the last element, and 9. All right. We are going to swap 14, or swap them. 9 is no longer in the heap. 14 goes 10, 10 goes to 11. Okay? And we keep doing this. Okay? Questions on the heap sort in place, how that actually works? I want you guys to understand this one. Not that I don't want you to understand the other ones, but yes, question.
Do you also need one more piece of memory to do the swap?
You do need one more piece of memory, but in this case, what could we use instead of the one more piece of memory? The 0. We actually got that one more piece if you want to use it. We could have said, how do we swap 10? How do we swap 10 and 14, right? We swap 10 and 14 by saying, oh, 14 goes here, 10 goes here, 14 then goes here. So you could write it so that you actually don't need no extra space in a heap. That's kind of cool. Kind of neat. Question? No? OK. All right. So what's the complexity here? Once we have it all done, this is what it ends up looking like, right? And by the way, how do you read it? You read it backwards. 2, 5, 8, 9, 10, 11, 12, 14, 22, and 43. If we wanted to be decreasing, we've got it already. If we want to do increasing, we could either read it backwards, or we could have started with a max heap instead of a min heap. All you need to do. Performance-wise, aha, n log n. Woohoo, right? You can build a heap in n time, and then to do all that swapping and everything is only log n time. That's kind of neat. Okay. And then average performance, or best performance, also n log n. Well, OK. Average performance, n log n. We've already said that n log n is really the best you're going to do on average anyway. You can get best cases that are better than that. But that means that this heap sort's a pretty darn good sort. So if you have a choice and you need to do a sort, heap sort's fairly easy to understand once you get down heap working and so forth. And it's also fairly fast, so not too bad. And it is completely in place, especially if you use the 0th element. Okay? You guys want to see that on the The fun video? All right, this was Heapsort. Let me back it up just a little. There we go. This one I don't believe is starting with a heap. I think it's starting with an unsorted array, but it'll heapify it first. There we go. Yeah, that's what it's doing right now, heapifying it. And then now it's doing the actual. Notice, backwards, right? It's doing it from the back forwards. Nice, pretty fast. All right, let's see what else we got. Oh, this sort's actually called a radix sort. We'll talk about that next week. This one is not a comparison sort, and it's really weird. Boom, it actually does it very fast the way it works. Radix sort is kind of a cool one. It's another type of radix sort by the most significant digit instead of the least significant digit. So it does integers by digit. This is also log n, I believe. Yeah, or n log n, I believe. Yeah. There we go. All right. OK. So let's see. What's this one? I'll stop on this one. I'll show you this one in a little bit. There we go. OK. So that is a couple different types of sort there. OK, so the last type of sort that I want to talk about is another interesting one. I think this one's kind of a pretty interesting one because of the way it works out. This one is called Shellsort. The first time I heard this, I didn't know anything about it. And I thought it had to do with, like, you know, you have like shells and you're like moving them back and forth. I thought it had something to do with that. No, the guy's name who designed it was Donald Shell, right? So that's why it's called Shellsort, named after Donald Shell. This is similar to Insertion Sort, but we know that Insertion Sort works pretty well on almost sorted data, right? And it works well for small data sets. But it's not particularly efficient. We've already seen that. It's not a very efficient sort. So what Shell did was he said, is there a better way to do this? Here's what he did. Okay? He said, and by the way, this is actually pretty easy to code and difficult to analyze. In fact, this is the one where the average time complexity is actually unknown, right? Like, we don't know what the average time complexity is for selection sort. For shell sort. If you, if you're like really into math and computer science and want to go get your PhD or something, you could consider looking at this. Although lots of people have, nobody's figured it out yet, and lots of people have looked at it, which could be good and bad, right? If you solve a problem that lots of people have looked at, that's great, but keep in mind that probably means it's very hard if people have already looked at it. But anyway, difficult to analyze. Here's the basic idea. Okay? Basic idea for a shell sort is you rearrange the element so that looking at every, this is impossible to say by the way, hth element, right, produces a sorted list, which is then said to be h-sorted. What that means is you're going to look at all your array. And let's say your what we call the gap, right? What we call the gap is, let's say it's 5. What we're going to do is we're going to take the 1st, the 6th, the 11th, the 16th, etc., and just sort those ones using an insertion sort. Okay? And then you're going to take the 2nd and the 7th and the 12th and the 17th, etc., and do the same thing. So you're sorting in these like gaps of areas. Okay? And then you'll see why that makes a difference in a few minutes. Once you do that, okay, once you've sorted all these the gaps for that particular gap, sorted them all, then we have said that this is now h-sorted. In that case, it would have been 5 sorted. What you then do is you go to your next gap down, and you've got to have numbers that are your gaps. And then what you do is you go and sort by that gap element. So in this case, the kth element. So let's say the gap was 3. You do 1 and 4 and 7 and 11, etc. And then you do 2 and 6 and whatever, or 2 and 5 and blah, 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 right? So you would do it that way. And then nice thing is, now it's going to be H sorted and K sorted. Doing the lower gap sort, which I'll show you in a minute, does not disrupt the previous sorting. Okay, so that's actually kind of neat. Continue going down until you reach a gap of 1, and you have to do 1, and then you just do a basic insertion sort on the whole array again. But now, because everything's already been kind of pre-sorted to a large extent, the insertion sort on that last one is very fast. Okay? What question does that consider? Yeah?
What's the best H value?
Yeah, what's the best gap structure? Very good question. OK, let's look this up. Let's see. If we go to here and then here, let's see. If we look up Shellsort, Shellsort. See all these here? Those are different people's opinions of what's a very good gap, right? Now, this is very mathy, all right? And take a look at some of these numbers. Like, you go backwards, by the way. This is like in the wrong order. You start at 120. So if you wanted to do this one, you start at 121, then you go to 40, gap, then 13, then 4, then 1. They all start at 1. They should all start at 1, okay, because you go back down there. And in this case, the order of the sort in that case, the worst time is n to the 3 halves, right? A little bit worse than order n, but it's n to the 3 halves in that case. Okay, not horrible, right? But it's like that, okay? There's lots of these, and if you want to go and do some more research in this and find a different gap for these, you could probably get a paper published, right? Some of these guys, like Sedgwick, did a few in a row here, right? That must have been his main area of research, was doing these things, right? Some of these in here, there's lots of them, right? Some of them in here, okay, so this one, right? It's totally unknown. What somebody just said, this looks like a good order, right? And then this guy, right? He's like, this is a pretty good order. Now, I'm sure he did some analysis, but whoever was putting this Wikipedia page together was like, I have no idea what the complexity is of this one, right? But lots of different ways to do this. If you are going to write a shell sort, go find one of these, find a pretty good one that you want to use, and then use that. Don't try to reinvent them, unless you want to do some research on it, right? Some of them, you might say, hey, what about sorry, one sec later. You might say, why don't we just divide by 2 each time, or something along those lines, right? Then, and this one's 2 to the k actually, but n4, this one's not so good. It's n squared. Not so great, right? Lydia, question.
When they say they haven't found the average complexity and the worst case complexity, do they is there usually can you find sort of estimates? Because I'm sure
Sure.
You could test it and it's they can't give you a neat math expression, but there's
Right.
average, working average.
Yeah. A very good question. The question was, can you find okay, so they don't have a formula that tells you what the average complexity is. Can you do it empirically? Sure, you can do it with anything. Anyone you can do empirically. Now, it might be n to the 1.635 or something that has you can't work it back and go, oh, it's it's something. But proving that would be the tricky part. For anybody in discrete math, right? Proving this sort of thing is part of the hard part about doing discrete math. You have to figure out how to get it down to that mathematical formula. But sure, you can if you wanted to go ahead and say, in fact, you guys ever heard of what is it called? Is it genetic algorithms, I think? Where you basically are kind of randomly permuting some algorithm in certain ways. This might be not a bad idea for a genetic algorithm to try to figure out a good gap sort, right? So you basically say, I'm going to kind of randomly choose some gaps, like crazy person down here at the bottom who, it's the unknown, right? I'm going to randomly choose these, and then I'm going to empirically test them against all sorts of different data sets. And maybe we check against the random, and we check against the partially sorted, and we check against, and then you publish your results. Not a bad paper, actually. Not a terrible idea. And it might already be done. I don't know, but not a bad idea in terms of trying to figure out empirically what the answer is. Yeah, we do that a lot when we can't do the math, right? Okay, so let's go back and actually look at how this works. Okay. Again, we're going to sort into these H-sort into these gap-sorted subsorts, and then we're going to repeat with the smaller gaps and see what happens. Okay. All right. So let's say we start out with the following numbers that are not sorted. Okay. By the way, I'm leaving it as 0 being empty. You don't have to do that for these. Sometimes the math's easier, sometimes it's not. But in the end, we'll just make a decision that right now we're just going to start everybody at 1. So first, we're going to do a gap sequence of 5, 3, and then 1. Why? Because it's easy. Right? We're going to just do it this way. Okay. First, you do the 5 sorts. So you've got to sort 1, 11, 6, and 11. And I tried to color code this. So color code this. 1, 6, and 11. And then we're going to do 2, 7, and 12. And then you've run out of space to do 3 at a time. So now you're only going to have to do 3 and 8, right? 3 and 8, and then 4 and 9, and then finally 5, 5, and 10. Okay, and those have to be sorted in those ranges. So the first thing we're going to do is we're going to look at 62, 17, and 25. And we're going to say, all right, it's got to be 17 here, and then 25 here, and then 62 here. And you can do an insertion sort to do that, because it's fast on relatively short arrays. Okay? And do the same thing through that list. All right? Now I'm going to skip like a bunch of steps here. I'm going to skip a bunch of steps in the sense that the actual individual gap sorting, I don't think you need to show you that, but it's just an insertion sort. But here's what you end up with. Okay, so the black here is the newly gap sorted to a 5 sorted array. And what I've tried to do is put the numbers up here what the originals were. Okay, so you can see that for the yellows here, 28, 83, and 95, it was 83, 95, 28, and now it's sorted in its proper place, according to the 5 sort. Okay, all right. Then we do the 3 sort. Now 3 sort, you're going to have to sort more, actually, as it turns out, because you've got 1, 4, 7, and 10, because you can do it. So you've got to do 1, 4, 7, and 10, and then 2, 5, 8, and 11, 2, 5, 8, 11, etc. Okay, it isn't until, in fact, this one, because there's 12 elements, you actually have to do 4 sets of 3. But once you do that, you will not screw up the 5 sorting before. Because you're always kind of sorting to the left, you are not actually going to mess up any of the previously sorted elements. Okay, work it out for yourselves if you can't figure that out. Try out a few cases and see that it works out. Okay, so once we do the 3, then we are left with this. Okay, the bottom one here is the previous one. Okay, now it's 7, 17, 7, 18, 47. You can kind of see it's starting to get more sorted, right? Like it's started to be more sorted. Kind of lower numbers are down on this side. Most of the higher ones are up on this side. That's good. And now we can do the 1 sort, which means go ahead and do the insertion sort for each one of these. 7 swaps with 17, and then let's see, 18 swaps, no, and then 18 remains the same, and then 25, like 47 doesn't, 28 doesn't, 25 swap, you know, etc. You end up with a sorted list. And you can just do a normal insertion sort at the end. It's already mostly sorted. End of story. Okay? Questions on that one? Yes?
So just when you're just sorting, let's say you're sorting every 5th element, what sort are you doing then? Are you just looking at 2 elements and swapping?
You can do, yeah, we generally do an insertion sort on those. Okay. Yep. If your gaps are huge, then well, it depends actually. If you have a large number of, if n is big, then you might end up doing a whole lot of insertion sorting, which is generally slow. But at that, in that point, you're probably better off to use a different sort for that one. But the point is, you can go and do that. Okay. So let's see. So that was insertion, or that was Shellsort. Where was I here? Oh, I got to pay my rent. I should have turned this off before. I'm going to send some reports. Okay. Don't ask. I've got more reminders than you want to know about. Now, by the way, the nice thing about Wikipedia, if you cared about this, you'd be like, hey, what did this guy actually say when he did this unknown business? What did he say? Right? The cool thing is you can actually find it online generally, right? And you can say this says the best increments for average case Shellsort. Not bad. Right? And this guy wrote a whole big mathy paper on this thing. Well, how many pages is it? Let's see. It starts at page 106 and goes to all on Shellsort, right? Whoa, this is a long one. 106, 117, so like 10 pages, right? And it, you know, you can see that he did lots of like probably empirical type of research on this. Yeah. Question?
Is there, this is kind of off topic, but
Yeah.
is there like, I don't know, like a format officially for like math papers like there is for like science papers? Because every like math thing I've seen at Tufts has been in that same font.
Yeah. Oh, yeah. So yes, there's good question. Is there a format for anybody know what was used to produce this? A thing called LaTeX or latex. Yeah. It's kind of a cool system actually. And you should probably learn it at some point in your life. Basically, it's how to write mathy kind of papers like this. And you can write anything. I've seen people write dissertations in this stuff, and I see people write paper. I used to write papers in this, you know, in the thing. What it is it's basically you write a text file, and it has all this kind of coding in there that you do. What's the coolest part about it for me is that you actually basically compile your paper, right? You type LaTeX, and it actually goes through it. It does all these like compilation steps, which is pretty cool. The guy who invented this, a guy named Donald Knuth. Oh, this guy, Donald Knuth, one of the most famous computer scientists ever, spent about like 4 years out of his career producing the program to make this paper. He thought that papers looked terrible back in like the 70s. They looked terrible. It used to be, side topic, used to be that way back in the day, like before the 70s, you would have a math paper and it would get typeset by a guy with like a machine where he took individual characters and like moved it down. Now, I mean, they had keyboards and things, but it was all hand to hand set, and they had different character sets for the weird like plus minus things and all different fonts and all that. And because it was hand done, it took forever, but it was looked very nice, right? In the 70s, kind of the mid 70s, late 70s, people realized that computers could help out with this. So the first people that tried this, like graphical, you know, using computers to do math publications, Donald Knuth tried to get one of his books republished using the computers, and it looked so bad that he said, I can do better than this, right? And so he started writing this whole program to do this, and he ended up taking like years out of his career to do it, but now we've all got the benefit of it. So anyway, yes, to answer, long story short, there is a general format. You can do it in Microsoft Word now, but if you see a paper that looks like this with this kind of font, it's almost certainly done in LaTeX. So yeah, good question. All right, so let's see. Back to the sort for a sec. So shell sort complexity. It can be as worse as n squared, right? Why can it be that? Well, you have to, even though you're doing the individual sorting, it might be in such a degraded state that you never actually get a very good solution such that the insertion sort at the end doesn't take a long time. It's not that. But you do get good performance in general. On average, our best performance is pretty good. Average, no idea. It's still an open question. But it is in place, except for maybe that one extra that you might need to do the swapping. Okay? All right. Now, this morning's class, I like totally built up this next little thing. And I'm like, this is the best video you'll ever see. Turns out you guys have already seen it. Or at least you've seen something exactly like it, right? By the same people who did this. So I think this is a pretty fun video that I'm about to show you. It's like 5 minutes long. And it's a visualization of a sorting algorithm. Yeah, you know, some of you guys know. If you took Comp 11 last semester, or probably over the summer or whatever, you probably remember this video, or at least one like this, because you did it in a lab. But let me show you what this is. This is a sort visualization done by this group in Hungary. Okay, let me turn the lights off for this. This is a shell sort. Whoops, wrong one. These guys are actually doing a shell sort. They had to memorize the algorithm and had to go ahead and do it. They did a lot of these. Actually, funny. I just went to was anybody else there today about there's a Hungarian exchange program that you guys can look into. It's actually kind of cool. It's a computer science one at a university in Hungary, in Budapest, I think, which is Hungary, right? So yeah. Anyway, if we look at all these guys, let's see. Let's see this person's video. So they did a quick sort, which has got to be crazy. I don't think I've seen that one. They did a merge sort, which we'll talk about. They did a shell sort, select sort. They do a bubble sort. Terrible. And then an insertion sort. So if you want to go look at all those, you can. Yeah. Right. I'm going to guess the bubble sort is at a higher tempo. because it doesn't take that much longer, but it's a really slow one. So I don't know. Anyway, that was the sorting. OK, so homework 4. OK, so homework 4, I will publish this by tomorrow. This is not going to be a particularly long assignment. Here's what you've got to do for it. But I tried to take some of the ideas from the feedback and apply them, hopefully in a way that makes more people happy. First of all, it's on sorting, which we're doing now, so it should be pertinent. Second of all, you're going to have to write 3 sorting algorithms. Okay? You're going to have to write 3 different programs, and they're going to be sorting. One has to be a selection sort. Okay? So one of your programs is going to be a selection sort. One of the other 2 programs has to be from the following list: Shellsort, Mergesort, Quicksort, Insertion Sort. We already discussed a couple of those. We're going to talk about Mergesort and Quicksort on Monday. Okay? But you have to pick from one of those and implement them. And you can't implement bubble sort or heap sort. We just did heap sort. And you can't do bubble sort because it's stupid. But not a very good way to do it. Although I suppose selection sort's probably just as bad. But anyway, selection sort's slightly more difficult to code, so whatever. And then your third one, you can choose another third one from this list. Okay, a couple of these are harder than others, but some of them are not too bad. So if you're kind of in the mood to like just kind of knock out this homework assignment and be like, okay, I've done it, I know a little bit more about sorting, then you can pick another. If you want a little bit more of a challenge, right, go ahead and look through the Wikipedia article for other strange, weird sorts. If you want to go try to implement the Tim sort or some like other kind of heap sort or quick sort that's got some other like weird algorithm in it, great. That's fantastic. And you can choose whatever you want for that. Here's how we're going to grade it. We're basically going to, it's going to be basically you do cin on a whole bunch of integers, and then you're going to print out the response, like the sorted list. Okay, not too bad. We're going to check all of your lists on various different types of input, like almost sorted, random, etc. Then we're going to time the results too, and that's kind of for 2 reasons. Number one, we want to see how well your sort actually does, but in terms of like the complexity. Number 2, we want to see if you've somehow, cheating's not the right word, but somehow done some other sort when you thought you were doing a certain sort. Like for instance, in your selection sort, it's going to be order n squared. Unless you do something wacky and completely wrong and use the wrong algorithm or whatever, and it ends up n log n, well then you've ended up with the wrong sort of sort. So we'll time it for those reasons. Okay? And if you end up with a type of sort that's like order n, unless it's one of the ones that, like if it was a bucket sort or something, might be harder. But if you we will time it for that reason. And then I thought it might be kind of fun to maybe, I don't know, give a shout out or maybe some prizes to people who got like the fastest overall sorts on their fastest sort. So we could do something like that. But anyway, I don't think this is going to be a particularly taxing one. But what I'll do is I will give you code that starts you off on selection sort. And then you will be completely responsible for writing the code for the other 2 programs. Okay, so you get the idea. You get to build your own programs from scratch. You can use the other parts of the other one to do it if you want to. But it's kind of going to be a little more open in terms of your ability to do, work harder or less hard on the assignment. Fair enough? Okay, question? I will at least start you on the read-in part. Although I do think you should be able to build a read-in. It's not that hard, but I will start you on that. Yeah, good question. Yep. Yuval.
For the ones where we pick our own sort system,
yeah.
Will we be penalized if we pick a sort system that's slower than the other one?
No. You can pick whatever sort system you want. I mean, like I said, don't do a bubble sort or a heap sort. It's kind of up to you. I think it's kind of fun to find a fast sort. I mean, sorting fast is kind of a big deal. But no, you won't be penalized by doing something that's slower. Yeah?
Would you shoot down BOGO sort?
Yeah, I would shoot down BOGO sort. So some sorts, would you like to explain to the class what BOGO sort or BOGO sort is?
Randomize it and then see if it's right, and then randomize it again.
Yes. Don't pick a sort that might take until the heat death of the universe to figure out. Okay, I would not accept. If your sort for all of our inputs does not finish in like 3 minutes, we will cancel it and say it doesn't work, right? So well, maybe not all of our input, maybe not the n squared one, but yeah, good question. So yeah, that's if you look at wacky sorts, there are some very wacky sorts. That's a great one. Where you basically, I've heard it as you take a deck of cards that you want shuffled, and you basically just throw it all up and pick them all up, and if they're in order, then it's sorted. If not, you throw them all up again and pick them all up and whatever. So yeah, same sort of thing. Yeah, very good. But yeah, so good, very good question. I should let the other class know the same thing. All right, let's see. On this, I do think I had some. Yeah, there's some references on this one. The Wikipedia articles are generally pretty good for sorting. The big one's good, and it shows all the different types of sorts you might want to do. There's lots of videos, Hungarian folks dances, and your textbook also has a whole chapter on sorting. Again, it's all right. It's good, but not phenomenal. Okay, questions? When's it due? I haven't quite decided yet. Probably a week, week and a half, but not too much longer because I don't think it's going to be that hard. Okay. All right, great. See you guys later.